Welcome back. In this class, we are going to talk about transmission gate and its symbols, and we will see some of the implementation using switch logic. Okay. Now, as you know very well, what is meant by transmission gate? In the last class, also we discussed this. Absolutely, the parallel combination of NMOS and PMOS is known as transmission gate. Okay. Will you please tell me what is the advantage of this one? Absolutely, there is a full swing. This is a major advantage present in the transmission gate. Is it clear? And what is the drawback? Absolutely, more number of transistors. Transistor count should be more. It is a drawback. Okay, more transistor count. Is it understood? Okay, and we will see some of the symbols of transmission gate, which is very important for your short question. Okay, what is transmission gate? What are the different symbols of it? As we know, the first symbol is very clear. The parallel combination is clearly going to be represented. This is PMOS, and you can observe this one. What is this? This is NMOS. Now it becomes an input. It becomes an output. Let us consider if it is S, it becomes S complement. This is the first symbol. And the second symbol you can observe, okay, the same symbol, this part is going to be removed, this part, and they are going to club with each other. Now you can observe these two, and if you observe that this is your PMOS, are you clear? And they are taking like this is your NMOS. Okay, now it becomes an input, it becomes an output. It is S complement. This is another symbol of transmission gate, and one more symbol of transmission gate is there, which is very different than these two. You can observe the third symbol also. Okay, now you can observe the third symbol of transmission gate. Now how it looks like, you can clearly observe. See carefully how I am going to draw. You have to take like this. Let us consider it is M, and bottom also you have to consider the same, and let us consider this is an input and this is an output. From here onwards you have to consider this one, then you have to call this one as P and this one as N. As usual, this may be input, this may be an output. If it is yes, then it becomes S complement. Is it understood? These are the three symbols of transmission gate. Okay, now we will talk about the implementation using switch logic. Is it clear? Now you can observe, we are going to talk about the implementation. Now you can observe one example I am considering here to implement 2:1 multiplexer using switch logic. Basically we know very well, okay, main classification of switch logics are pass transistor logic and transmission gate logic. You can observe very clearly, I have considered 2:1 multiplexer as an example. Let us consider I0 and I1 are the inputs of a multiplexer. S be the selection line and Y be the output. Now you know very well that when S is equals to 0, I0 is going to be transmitted to Y. Therefore the output is I0. If S is equals to 1, then I1 is going to be transmitted to the output Y. Therefore the output is I1. Is it clear? Now before going to implement this in switch logic, you can observe in gate logic how it looks like. Okay, now you can observe in terms of gates I am going to draw. You know very well what is the Boolean expression of a 2:1 multiplexer. Absolutely, Y is equals to, if S is 0, let us consider S complement, then I0 should be selected, else if S is 1, I1 should be selected. Okay, based on this you can observe it is S. Let us consider this one S complement. Is it understood? And if you observe that if S is 0, which one is going to be selected? I0 is going to be selected. Okay, therefore let us consider this one like this. It becomes S complement into I0. Now if you observe that if S is 1, which one is going to be selected? I1 is going to be selected. Now you can observe that what is this one? S into I1. Are you clear? And these two are going to be connect to whom? an OR gate, and you can call this one as what? Y. Now you can observe basically what are the gates you are having. One NOT gate, next 1 and 2 AND gates, and one OR gate. And we know that how many transistors required to design one NOT gate using CMOS. Anybody? Absolutely 2 transistors. For each AND gate you require absolutely 6. Therefore you require 12 transistors, and here you require 6 transistors. Then you can observe 6 plus 12 plus 2, which is equals to what? 20 transistors are required. Okay, I hope that are clear. How many transistors? Anybody? Absolutely 20 transistors. Now this is going to happen in gate logic. If you talk about the same concept implementation using switch logic, you can observe how it is going to be. Okay, now you can clearly observe. Okay, 2:1 multiplexer. Okay, first I'm going to focus on using pass transistor logic. Okay, now observe very carefully. This is my pass transistor, and this is my one more pass transistor, and we required a common output. Therefore I have to join these two, and I can call this one as Y, I can call this one as I0, I can call this one as I1. Now you can observe that I am considering this may be S complement and this may be S. You can verify the functionality. Okay, now let us consider S is equals to 0, this case. What about Y? If S is equals to 0, this will be in off condition, this will be in on condition. Therefore whatever the value present here, that will flow to Y. That means Y is equals to I0. Is it clear? Now you can observe the another condition. S is equals to 1. What is Y? You can observe that. Absolutely. When S is equals to Y, you can observe that this transistor will be turns off and this transistor will be turns on. Therefore there is a path like this. Then what is an output? Absolutely I1. That's it, guys. That means you can observe how many transistors are required. This is 1, this is 2, and don't forget a complement 2. That means totally 2 plus 2. How many transistors? 4 transistors are required. If you compare that, where is 20 transistors and what about 4 transistors? Is it clear? This is the variation present in the number of transistors using switch logic. Especially here, which logic we are talking about? Pass transistor logic. But what is the drawback present in pass transistor logic? Can anybody try to tell? What is the drawback present in this multiplexer? Anybody? Absolutely. What is that? No full swing. Is it clear? If I0 is 0 and I1 is 0, we do not have any problem at all. When I0 or I1 is equals to 1, then there is a drop present here. Is it clear? There is a drop present here. What is that? I0 minus, that means we can call this one as VDD. If I0 is equals to 1, then what is an output present here? VDD minus VT. That is, there is no full swing at all. Is it clear? This is a major drawback present in this pass transistor logic, especially not a switch logic. Now we are going to observe how this pass transistor logic is converted as transmission gate logic. Now I am going to talk about 2:1 multiplexer using TGL, that means transmission gate logic. Is it clear? Now you can observe in the pass transistor we are having this circuitry, right? Okay, this circuitry we are having in the pass transistor. This is S, it is S complement, it is I naught, it is I1. Now you have to replace each and every pass transistor with the transmission gate. Now you have to replace this. That means here you require one. Okay, I will use the second symbol. This is one, and you have to replace this one. Okay, here, sorry for that, I will use a short length. Okay, now you can observe I'm taking oppositely. Is it clear? Now you have to join these two, then you can call it as Y, and it may be I naught, it may be I1. What about this S complement and S? Here you can observe very clearly S complement is given to whom? NMOS, therefore it may be S complement. Is it clear? Is it understood? That is an important point you have to talk about. Okay, and can I consider in this passion, such a passion, if you observe that, if I can consider in this passion, I can consider in this passion, if you observe that very clearly. Yeah, yeah, in this fashion. If I consider this one like this and this one like this, you may observe very clearly what is happening there. Why? Because how to give the control signal, that plays a major role. In I naught, for NMOS, S complement should be present. Therefore here S complement should be present. In the I1, for NMOS, S should be present. Therefore this becomes what? S. And don't forget, if this is yes and this becomes also yes. I hope that are clear. Once again I am explaining, very carefully observe. Here in the I naught input for NMOS, what is given? S complement. Therefore for I naught, for NMOS, you should give what? S complement. Similarly for I1, what is given? S is given. Therefore for I1 input, for NMOS you have to give S. Therefore I am joining these two and common S complement is given, and this is S and this is S. Now you can observe that if S is equals to 0, what is happening? Now you can observe that if S is equals to 0, what is happening means this transistor will be turns on, and the same time this is also turns on. Therefore the first transmission gate is going to be turns on. What about the second transmission gate? You can observe it will be turns off. Therefore what is an output? I naught is an output. Is it clear? Since it is a parallel combination of both NMOS and PMOS, the output is full-fledged. If I naught is 0, the output is 0. If I naught is 1, the output is 1. Similarly, if you observe the second case, if S is equals to 1, what will happen? That means the first transmission gate will be turns off, the second transmission gate will be turns on. Therefore there is a path to Y. That means Y becomes what? I1. Is it understood? This is one of the implementation using switch logic. Is it clear? Now I'm giving a task to you. Try to design 4:1 multiplexer. Okay, 4:1 multiplexer. This is the task to you. I hope that are clear. If you are having any doubts, please comment. Is it understood? Thank you very much. Have a nice day.